I'd like to thank everyone involved for organizing this event, especially the chair of the Lytle Lectureship Committee, that's Mariam Fazal, who holds the Morthy Family Professorship. So thank you, Mariam. Professor Fazal is also the UW Associate Chair for Research, and she leads the NSF's new Institute for the Foundations of Data Science, which brings together mathematicians, statisticians, computer scientists, engineers, and so on to develop the theoretical foundations of data science. Let me tell you a little bit about the Lytle Lectureship. So the Lytle Lecture Series honors the memory of Professor Dean W. Lytle, who began his career as an assistant professor in our department in 1958. He was a beloved teacher, mentor, and intellectual powerhouse in the department. Professor Lytle's research focus was in communications, networks, probability, and signal processing. He authored 2 textbooks, and his consulting work included appointments at Boeing, Honeywell, and Bell Telephone. The series was established in 2006, which was the centennial year of our department, through fundraising efforts led by Louis Scharf, who I believe is here today, in collaboration with Muriel Lytle and the Lytle family. Dean's graduate students, his colleagues at Honeywell, Marine Science Center, and the UW ECE community all contributed to this, to the endowment to make this lectureship possible. So I would like to thank all of those who have contributed to support this effort and make this lectureship a reality. So thank you very much. Next, I would like to introduce Professor Radha Puvendran. He is a professor in our department for 21 years, and he's the former chair of our department. He's the director of the Network Security Lab, and his research focuses on wireless and sensor network security, adversarial modeling, privacy and anonymity in public wireless networks, and cyber-physical system security. So please welcome Professor Puvendran, who will offer a few remarks about our invited Lytle lecture speaker, Professor Muriel Médard.
Thank you, Eric. Good afternoon to everyone. It's an honor to introduce our distinguished speaker, Professor Muriel Médard. I've known Muriel for more than a decade, probably close to 2 decades. Professor Muriel Médard is a Cecil and Ida Green Professor in the Electrical Engineering and Computer Science Department at MIT. She leads Network Coding and Reliable Communication Group in the Research Laboratory for Electronics at MIT. Her work lies in the intersection of information theory, communications, networking, and security. Professor Médard earned 3 bachelor's degrees, a master's degree, a PhD degree, all from MIT. She also holds an honorary PhD from Technical University of Munich. She's a member of National Academy of Engineering, Fellow of the National Academy of Inventors, member of the American Academy of Arts and Sciences, and a fellow of the IEEE. Her research emphasizes developing new theoretical results and implementing them in engineering systems. She has over 50 US and international patents. Vast majority of them have been either licensed or incorporated into other systems. She's a co-founder of Code-on Technologies, which commercializes random linear network codes. And she's also co-founder and chief scientist of Steinwurf. This commercializes forward error correction codes. For her contributions, Professor Médard has been awarded numerous recognitions. A sample includes 2022 IEEE Koji Kobayashi Computers and Communication Award, 2018 ACM Special Interest Group in Communication Test of Time Paper Award, 2009 IEEE Communication Society and Information Theory Society Joint Paper Award, and many more. The list is long, but I take some samples to highlight the contribution and the impact. In addition to technical research, Professor Médard is also a dedicated mentor, and a community leader. She's a founder of Women in the Information Theory Society with its. She's the founder of the Information Theory Society Mentoring Program, and she served as an undergraduate faculty in residence for 7 years in 2 MIT dormitories. She received the Simon's Outstanding Mentor Award for her work with high school students. In 2013, she received the MIT EECS Inaugural Graduate Student Mentor Award, selected by the graduate students of the department. She was also the president of the Information Theory Society in 2012. So we are glad she was able to find time to be our distinguished speaker today. Please join me in welcoming 2021 Dean Lytle Distinguished Speaker, Professor Muriel Médard.
Thank you very much, Radha, for such a kind introduction, and Eric also for your the introduction at the start. And I want to thank Miriam and the entire Lytle lecture team for this invitation. It is a huge honor. I've also had a chance to meet briefly with the Lytle family before this. And as I told them, I think that the work is definitely in the intellectual legacy line of Dean Lytle in the context of communications networks and bringing together probability signal processing and circuits and applications. So I hope to convince you that it is in that intellectual line, and I look forward to your questions. Okay, so the title of my talk is Deviation from the Standard. It's a intentionally playful title on standard deviation. Many of us have been hearing about standards. You know, these are usually things that are going on in the backgrounds that you don't really hear about in the news, or, you know, maybe very seldom. And it's been rather a surprise, I would say, as an engineer and to many of us, to see these kinds of discussions happening in the public domain, in the popular journalistic discourse. And a lot of this, of course, has revolved around 5G. You know, what is 5G? What will it do? What does it do? Where is it? Where isn't it? What will it not do? And this idea that the standards are very much crucial to 5G is one which I'm going to try to present today is maybe a waning one, or one that will no longer be needed as we go forward. I'd like to acknowledge my two main collaborators on this work. One is Ken Duffy, who's the head of the Hamilton Institute, Applied Math Institute at Maynooth University in Ireland. All of the algorithmic and theoretical work is with him. And also I'd like to acknowledge Rabia Yazicigil, who's at Boston University. All of the circuits work has been with Ken and her. Okay, so what is the evolution that we've been seeing in networks? Why is it that every so often we get these different generations, you know, again, 5G being the latest flavor of these generations of mobile communications? Well, the evolution that you can see is one of, you know, increasing complexity, you know, and increasing heterogeneity and diversity. So, you know, the idea was that normally people would have, you know, a device, say a phone, but maybe a tablet or whatever it may be, and that spoke to some access point, which was maybe a base station, or maybe what we call, you know, microcells, maybe like a point of access for a fairly small geographic area. There was a link, usually called the backhaul, that sort of got you to the core of the internet. And then that would somehow get you to wherever the content that you were trying to access was. Okay, there might be a little bit of what we call device to device, which is basically maybe, two phones talking to each other using Bluetooth, but that was just pretty much happening on the periphery by itself. Increasingly, things became more distributed with respect to where the content was being kept. You saw more and more what we call caching, that's to say content being duplicated, being placed in many different parts of the network. So this little iconography that you see here, these are actually little iconography for storage, for memory. They look like little discs. And so, it became something where the network was maybe more distributed, decentralized as to where the data was. This is often what we call now the cloud, or the cloudification of services, where you basically, may store, say, your music that you want to hear on your personal device somewhere in the cloud. You maybe don't have it on your device, but you have it, in storage, with the understanding that, of course, it's not kept in a single location, that it's being accessed from a variety of copies or pseudo copies, which I'm not going to talk about today. So there's a lot of this pushing of the data to the edge, a lot of these small stations, and then increasingly now with services, it's no longer just accessing data, but also accessing computing. Okay, so when we talk about the cloud now, we also talk about computing in the cloud. That is to say that, a huge amount of the services that I obtain from my phone are actually being powered by machine learning algorithms that are trying to divine my needs, that are trying to provide me services such as, for instance, Google Maps, so I can get around and find things easily, or other services which are basically intrinsically computing services, again, in a distributed way. Okay, so this is sort of a cloudification of everything. So in this very interesting, setting that we have here, what can I say about the wireless part? And what can I say about where the communications comes in? Well, the communications is crucial because all of this cloudification, complication, distribution that's occurred is pretty much not going to have any real effect unless, of course, I have the ability to connect, say, with a wireless link. Okay, and that ability to connect with a wireless link is going to be crucial, and it's really what I'm going to be talking about today. So, what does this wireless link need to give me? And by the way, I think the permissions just changed, so I think I was able to do annotation before, but it's not clear that I can do right now. Something just happened. So maybe if I can get presenter mode, that would be great. Thank you very much. So what do I need from this wireless link? So we've heard a lot of this, again, in the context of 5G. And as I said, 5G formally is a set of standardized technologies. But of course, the reason why you have these standardized technologies is because there is a need. And that need is the informal understanding that, again, can be found currently in the popular literature, in the popular discourse around this ubiquitous technology, communications. Now, there's many different aspects to that. There's the integration across technologies, integration with the cloud, the cloudification, which I've talked about, and which I've given many talks about before, but I'm not going to emphasize today. But reliability, and also the low delay. Okay, when we think about when we think about augmented reality and virtual reality, when we think about, having 5G maybe be involved in self-driving cars, you need reliability, but you also need to have that happen with low delay. And that's actually, we'll see, very, very difficult to achieve simultaneously. So this current need of, accessing this very rich cloud with wireless systems, this current need is what we generally denote in industry URLLC. Now, it doesn't sound particularly euphonious, but let me break it down. It's ultra reliable. We need it to be reliable because, again, if some of these services are going to become, in effect, essential services, such as virtual reality, which is not just for gaming but integrated into real world services such as self-driving cars. We need that to be very reliable. And we also need it to be low latency. Okay. And the problem is that these two desiderata have generally been working against each other. To do the ultra reliable part, we have two main components in our toolbox. One is coding at the physical layer, and I'll describe in this lecture what that means. The other one is transport protocols, which are protocols for managing at the higher layers, sort of a little bit more in the cloud, what's happening, how data is being transmitted. Many of you may have heard me talk about these transport protocols, particularly in my work in network coding. And Radha very kindly overviewed some of the work that I've done there in tech transfer for transport protocols. But what I want to talk about today is the first aspect, the coding at the physical layer. Again, we'll go into what that means. The problem is that that set of tools which have worked towards enhancing reliability have come generally at the very much at the cost of the low latency. So we've been, in effect, adding reliability by adding more and more layers of robustness mechanisms. And those robustness mechanisms have been working in a way which actually slows down our services. So what has the general approach to this been? We'll go in a little bit and see how people get around this. But let me mention what I mean by physical layer reliability, this coding at the physical layer. So if I give you some information, and I'm going to provide that information to you in a machine understandable way, say in binary using bits, I may give you a string of characters. Say I have a string of 8 characters, the string that I have there on my slide. But there's going to be noise. I've talked, for instance, about a wireless link. Somebody was using a phone on the same frequencies at the same time. Somebody turned on the microwave oven. Something went a little funky in the circuit. Maybe I'm using a satellite link, and there's all sorts of interference and deleterious effects that come and add themselves. And this additive model is a very common and often very powerful one of adding noise. But for whatever reason, the last bit, which was a 0, I heard as a 1. Now, if you could have told me any combination of 8 bits, we're doomed, right? There's no way that I could know that you didn't actually mean to send me this other string of bits, which just happens to have a 1 at the end. So what we're going to do is we're going to agree on a code book. And we're going to agree on the fact that certain things that I receive are not going to be okay, and that therefore that will immediately prompt me to query what it was that you actually sent. So if I hear this message with a 1 at the end, and I go, there's no way that was what was sent to me. That doesn't make sense to me. That's not part of the code book. That doesn't check out. Then I'm going to try to correct, that's what error correcting codes are, and I'm going to try to correct what I received and see if I can recover the originally transmitted message. Okay, and in 1948, Claude Shannon, who was at Bell Labs, a place where also did Lytle spend time, and later was a professor at MIT, came up with the channel coding theorem. And the channel coding theorem said, how dense can these code books be while ensuring that decoding errors are rare? Okay, so I can see that they cannot be fully dense. It can't be that all possible transmissions are legitimate. Otherwise, I'm doomed. But of course, I don't want to have only one possible thing to send. Otherwise, it's not a whole lot of information, a lot of variety in the transmissions. And coding is a construction of code books and computation-efficient mechanisms for decoding, for mapping a received string, say the string that I got here, back to an element of the code book. Okay. Now, given that that is what code books do, what would be the engineering need? Well, we just saw that in particular with the current generation and future generations, there's a desire for low delay, low latency. So that would mean that I would generally like my code books to be short. I don't want to have to wait for, thousands and thousands and thousands of bits to figure out what the message was. I'd like to make my decision as quickly as possible. I always want to have low complexity. I want to have something that's lightweight. I'd like something that's flexible. Flexible, that means in how long it is, so that it can be adjustable to the different situations that I find myself in my communications, and also in rate, that maybe sometimes I need to change the operating regime. And of course, I would like everything to be robust to the physical reality of noise in systems. And the noise in systems tends to be messy. I mentioned the microwave. The microwave is on. It's going to be on for a certain amount of time. If I'm getting interference from a different device, that interference may actually take a duration that is not just the transmission of a single bit. Unfortunately, the mathematical models that we have that have come in effect from this initial work from Shannon in 1948 have sort of oriented us towards a very different model of solving the problem of robustness. We go for long codes. N is generally going to be how we denote the length of the code, the number of bits that I'm sending. In the example that I just showed you, N was 8. We take these large limits, and the reason we do that is because if you take a very large size, you have something that we call that we generally refer to as going to the mean. Okay, so we got concentration around the mean, concentration onto an average behavior, but at the cost of a lot of delay. Code constructions are often very constrained in length and rate. I'll show you some examples, but I encourage those of you who are interested in attending my second lecture today, which will be a little bit more specialized, and where I'll give you more examples of these constraints in length and rate. And we have very complicated code-specific decoders that are highly tailored, entirely bespoke to ensure feasibility, often at long lengths, because these long lengths, by the way, also entail a lot of complexity in the processing of the received code words. And you have just a staggering number of them. The only reason I give you some examples here is, if you're in the field, it means something to you. If you're not in the field, what you should see is, this is a mess. Okay, this looks like letter soup. What the heck is CASCL? Oh, CRCA did, successive cancellation list decoding. What is an LDPC? Low density parity check code. I mean, anything that has these many names and these many acronyms is highly, highly complicated. Now, the way Shannon had told us to build code words was not like that, by the way. The way he had told us to build code words was fairly different. His idea was actually very, very, very simple. and I wanted to be able to annotate, but let me see. Don't think I can annotate.
It may be a feature
oh, no, I
that
can. Pardon?
I've made you co-host, so you should have that ability. And if it's not there, it's a feature that UW has disabled itself.
Okay, perfect, no problem. I will, okay, so sorry, I'm used to the MIT system where I usually annotate, but that's no problem. So let me just highlight this part here, which is, so if I have a length n binary string, that means I have 2 to the n possible strings. And the way we usually look at the efficiency of my transmission is when I send a string of length n, what ratio of the bits that I've transmitted are bits that were originally there in my message? What is the payload? Okay. Now we saw that I can't have that. If I have a string of 8 bits, all 2 to the 8 are possible, because otherwise I'm going to have no error correction capability. So the rate is the proportion of extra bits that I'm going to have to send. So if I add those extra bits that I'm going to have to send for reliability, and I divide them over the overall, so if I divide just the bits that are payload over the overall number of bits that I've transmitted, that gives me the rate. So suppose that I have to send for every 8 bits an extra 2 bits. That means that it's 8/10. My rate is then 4/5, and that's what my R is. Obviously, I want my rate to be as high as possible. What that means, by the way, is out of 2 to the n strings, a code book is going to have only 2 to the n R possible messages. So even though I have a ratio of bits, when I look into the number of strings, if I take 2 to the nr and I divide it by 2 to the n, r being less than 1, the ratio of possible strings to all possible transmitted strings from my messages to overall strings on my codebook is going to 0. Okay, so I'm having a density of possible messages that is going to 0. My possible messages are becoming extremely sparse, while at the same time the ratio of bits is being kept constant, which is one of these reasons of going to this large n. Now, I want this rate to be as large as possible. And as I said, in 1948, Shannon identified the maximum rate at which communication could take place if one knew the statistical properties of the noise. And if I have bits, then that rate is going to be 1 minus h, where h is a statistical measure of the noise, which we denote by Shannon entropy h, which is actually the entropy. Okay, and if you've taken, for instance, any sort of physics courses, this is actually very related to that kind of entropy that you may have encountered there. If you haven't taken any physics or any comms or so on, think of the entropy as just a statistic, just like a mean statistic of behavior of the noise. So what was Shannon's idea for the channel coding, which was not to have this letter soup that I just told you, both in the construction of the code and in the decoding. His idea was actually bizarrely simple, but really very much based on this idea of sparsity that I mentioned as the n gets large. Okay, he said, take all the messages that you want to send, okay, and there's 2 to the nr of them. So for instance, if I started with 8 bits, there's 2 to the 8 of them. If I'm adding 10 bits, it's going to be 2 to the 10 possible code words. I'm going to take a big bag and fill it with all the 2 to the 10 possible code words. Okay, so I have this big bag, and then I have a shelf with all of my messages, all my 2 to the 8 messages. I'm going to take the first message and I'm going to dip my hand into the bag of 2 to the 10 with 2 to the 10 code words. And I'm going to randomly, uniformly pick one. I'm going to assign it. I'm going to have a ledger where I mark the assignment of that particular string of 8 bits to a particular string of 10 bits. I'm going to put aside my message. I'm going to take my string of 10 bits, stick it back in the bag with replacement, take the second message, dip back in the bag, do the assignment, note it on my ledger, and so on and so forth. Okay? And that's the construction of the code book. By the way, you note the time of Shannon's 1948 paper. This is right after, of course, the Second World War. He had been involved in code breaking, something that we often associate with Turing as part of the Enigma code breaking. This was something that Shannon had himself been involved in, and so I don't think it's a coincidence that we have this idea of making a code. Okay. Now, how is the decoding going to happen? Well, the decoding is going to happen in the following way. The receiver is going to have the ledger that we just created and is going to have the ledger there as a reference. The receiver is then going to see a noisy version, which we usually denote by Y, which is of length N. So for instance, if we had 10 bits, the receiver is going to hear 10 bits, and some of them, like we saw in the example before, some of those bits might be flipped. The receiver is then going to go through every item in the ledger and say, what is the item that maximizes the probability, P here denotes the probability, of having observed what I observed, okay? All the messages, by the way, are assumed to have the same probability. There are many good reasons why that's true. Generally, you have some pre-processing, which we call source coding. Again, if you're interested, please come to the second lecture. We have some pre-processing. This is source coding, which actually makes it reasonable to have that assumption. Okay, so all of the original messages are a priori more or less as likely, and therefore it makes sense when looking at the Y at the received signal or interpretation of the signal to figure out what was the most likely of the inputs of the original transmissions that would give you that observed signal. Okay, and that's the maximum over the entire code book of this, right? Now remember, my ledger is huge, right? But the sender and the receiver have shared this ledger. Okay, so why don't we do what Shannon suggested we do? Why do we have this letter soup, a letter soup of things with, lots and lots of words in them? Okay, there are two difficulties. The first difficulty is in the ledger that I said. The ledger would be huge. I was saying 8 bits, 10 bits, but remember that he wanted N to be large because of that sparsity argument. So if N is, say, 1,000 bits, and, a lot of modern code words are multiple thousands of bits, and you want the R to be large, of course, you want the R to be as effective as possible, then 2 the NR is massive, okay? I mean, we're talking unmanageably massive, okay? So you can't store that ledger. The second was the computation. Remember that the receiver has the ledger and then has to go through the ledger and figure out what was the most likely input given the output that was, that would provide the output that was observed. The complexity there is also unmanageable. So because of that, what we've done is we have really developed a very rich, intellectually sophisticated, and highly specialized area called coding and decoding. Block and convolutional codes from the 50s and 60s are basically just linear mappings from inputs, basically putting them through linear transformation that expand them into larger strings. Modern codes, I put them into in quotation marks, sort of were rediscovered in the 90s. I put them in quotation marks because they include low density parity check codes, LDPCs, that I mentioned before, but those actually had been developed by Bob Gallagher, my thesis advisor at MIT, in his PhD thesis in the early 60s. So they're not exactly modern. They've been around for longer than I have. Turbo codes appeared from Université Bretagne in France by Bérou, Glavieux, and Téti-Majima in the early 90s. Those actually, interestingly, did not come from people who would have considered themselves coding theorists. They came from circuits people, go circuits. And they were looking at coding as amplifiers, and they thought of amplifiers as balancing amplifiers, coding as, the notion of balancing amplifiers. Rateless codes and network codes basically came really at the higher layers, usually more around erasure correction. And then in 2009, polar codes come along, and they were discovered by another student of Bob Gallagher, Erdal Arakant at Bilkent University. And they're the first codes that were structurally shown from scratch to be capacity achieving. The modern codes, LDPCs and turbos, were empirically capacity achieving, but there wasn't a full characterization of their ability to reach that 1 - h that Shannon had told us about. The block codes and the convolutional codes, by the way, do not get us that 1 - h. Again, come to the second lecture today if you want to know a little bit more about those. Okay, so remember that there were two difficulties behind Shannon's idea. Difficulty number one, how am I going to keep track of this ledger? Difficulty number two, even if I kept track of this ledger, how am I going to go through the ledger in order to do my decoding? The first difficulty actually has been obviated since the early 60s, since the early 70s, late 60s, again by Bob Gallagher. He showed that you could just use linear codes, and a few other people sort of showed similar results. So I'm assigning it to Bob, but we can talk about the right assignment, and I'm sure Louis, who's in the lecture, can tell us more about that. But basically, it wasn't the ledger that was so hard. That sort of random assignment could instead be done by having a single random linear matrix and passing the original 8-bit strings through an 8x10 matrix to get 10-bit strings. So the first part is not the real difficulty. So the only difficulty that remains is the second one, which is the computation. So the reason we do these complicated codes is not, and these constructions, is not because of the ledger part. It's because of the decoding part, the reconstruction part. Okay, so this random linear is actually capacity achieving and has been around for a long time. It's just only been considered just as an ontological tool, just as a proof technique, rather than as a possible coding mechanism, because of this problem of how do we do the decoding. All right. So, given that, what are we doing and why? And we've been spending a little bit more time now with 5G thinking about all the things that we want to do. But what are we actually doing and why are we doing it? So if you look at what we're doing now, we're doing high redundancy codes. So we're actually, even when we use codes that are capacity achieving, we're not using them at capacity. And we're doing code-specific decoders because remember, the complexity is actually in the decoding, and it's the complexity in the decoding that's leading us to do these high redundancy codes. Now, remember, high redundancy codes means I'm sending bits I didn't need to send, and that means that I'm actually being wasteful in energy and in time. Okay. What I mean by redundancy codes, bit flip probability, the probability like I showed you before, going say from 0 to 1 or 1 to 0 in cellular mobile communications is very low. It's around like 1 in 1,000. Means that the capacity, if you compute this H of the bit flip of the noise effect, it's very big. It's like over 90%. 1 - H is over 90%. If you look at how we actually use codes, say in 5G, in the new radio standard, you're looking at, instead of over 90%, 50%. 30%, sometimes 20%. You almost never break the 90% barrier. So we are wasting a huge amount of spectrum. We're wasting a huge amount of energy in transmission and reception. And the reason we're doing that is because we insist on using certain kinds of codes, because those are the only ones we know how to decode, because we have these coding specific decoders. So what does this mean, going back to ultra reliable low latency, is in order to get around the fact that we have these long codes and that we're wasting a lot of transmissions, what do? We transmit more, we transmit faster. And how do we do it? We add spectrum. Okay. It's not so much about data rate, it's about speed of delivery, this reliable, this low latency. So one way to get the speed of delivery is just to keep doing everything faster. Okay. I like to, it's basically like, think of doing something and just putting it into fast forward, right? So it's like, you just speed up everything. You add spectrum, do stupid things faster with more energy. All right. So, we're running around literally just sampling faster and faster and faster. And it's hugely expensive. If you look at the latest FCC auction of 5G spectrum, we're talking about tens of billions of dollars, a good chunk of which is just being thrown down the drain. Okay, because if you're going at 30%, which should be going at 90%, it means that at least a third of the spectrum, at least 2/3 of the spectrum you bought was wasted. So you've wasted several $billion. Okay. These code-specific decoders, therefore, have much to answer for. And if you look at how they're chosen, much of the recent debate on the adoption of 5G wireless technology has centered on the issue of standards for error-correcting codes. The decoders are generally not included in the standards. They're left up to individual companies to pick. But de facto, what's happened is because of this code-specific decoders, once you pick the code, there's only a certain family, a certain range of decoders that are feasible. Okay, and this justification has always been based on the historical presumption that error-correcting codes require specialized, complex decoders implemented in dedicated and very fast chips. Okay, I'll give you already some examples. Here's some more examples. And in effect, we're fixing the codes because we need to fix the types of decoders, not the exact decoder, but we say, I'm going to send you a rate 1/3 LDPC because you will have a decoder that, by hook or by crook, is going to be a belief propagation decoder that is specialized to LDPCs, a particular set of LDPCs of rate 1/3. And we're only going to have a few choices. So again, it's the complexity of the decoder that's actually creating the need for standardizing the code. And that's why we're throwing billions down the drain, literally, because otherwise we don't know how to decode. Okay, so it's really even though the decoder is not fixed, it's the need to have decoders matched to certain codes that is creating this need for standardization. Okay, so we code data to avoid corruption by noise because we need that reliability, and we have code-specific decoders. Say, Bose-Chaudhary-Hockenheim code may have a Burley-Camp-Massey decoder. Reed-Muller codes have, say, majority logic decoders. Polar codes have successive cancellation algorithms. CRC, cyclic redundancy check codes, which are there just to check for errors, are usually not even there, but they're not even used for error correction. Random linear codes that Gallagher had given us at the end of 60s, beginnings of 70s. Up until now, we didn't even have a decoder. Okay. And I remember when I presented the algorithm that I was going to tell you about the first time, former president of our society said, well, what kind of codes do you think you can decode that? I said, RLCs. And he laughed, like loud guffos. Okay, not just, not even a smirk, just peals of laughter. And basically what happens is we have this proliferation of chips for different codes and sometimes even for different rates within the same family of codes. So in this, what I'm going to do is provide a different approach, which is guessing random additive noise decoding. which we call grand. Now, if any of you have spent more than 5 minutes in Ireland, where Ken is, you know that everything's grand. So grand is fine, it's great. You say, how are you? They say, you're grand, and everything's grand. It's like, the catch-all phrase for anything that's going on. And we're going to make the math work like the engineer. We're no longer going to assume these super high ends that came to us from, post-World War II. We're going to be doing things differently. So here's the chip that we have created. And what does the chip do? So remember, I told you about why the received signal. It's the combination of what was sent, the message that was sent. The message that was sent, the code word that was sent, we said is of length n, right? Say we went from 8 to 10, but there's only 2 to the n-r of them. So they say only 2 to the 8 of them, even if n is 10. And then we have an addition, which is often not necessarily an addition in the reals of the complex. If I'm looking at bits and an addition modulo 2 in the bits and Galois field of size 2, whatever it is, it's an additive. We generally denote the noise effect, which we usually call by n, as an addition. Okay. And this entropy of the noise that I told you about when I told you about Shannon's theorem of 1 minus h is the maximum rate. This h, which is the entropy of the noise, actually also indicates what is the size, the cardinality of the strings of noise that I'm likely to encounter. And it turns out that if I have an entropy of h, then with high likelihood, I will only have a set of noise realizations, of noise effects on my input x that was transmitted of size 2 to the nh. Okay. So if n is large-ish, say even if it's 1,000, and r is large as we want it to be, say around 0.9, good luck looking at all these code words. That's why we have all these specific decoders and all these specific encoders. I can't just take the ledger and decode. But let me look at this one. If I have these bit flip probabilities that I told you about, say about 10 to the minus 3, it turns out that h at these low probabilities is roughly the same, is of the same order as the bit flip probability. You can just do a little Taylor series expansion. Any of the undergrads in the audience can do it, okay? And that h is also around 10 to the minus 3. So if n is around 1,000 and h is around 1 in 1,000, then nh is about 1, and 2 to the 1 is 2. And that's also like 1. Okay, so there are not a lot of choices for this with high likelihood. There's a lot of choices for this first guy. There's not a lot of choices for this second one. And so the identification of the most likely code word sent can actually be written in this way. You take as an input the y, what was received, and some code word membership test, anything. Think of a hash. Just telling you if something's okay or not. I'm hoping this will appeal also to all the computer scientists in the audience. I'm basically going to look at a noise effect, say bit flip. Maybe you think the most likely bit flip to have happened is at the end. Very often that's the case. Maybe at the beginning, maybe in the middle, maybe it could have been anywhere. But whatever is the most likely noise effect, I'm going to subtract that noise effect from the received signal. I'm going to try to undo the noise effect of the most likely noise. If the resulting string is in the code book, eureka, I got the right code book, the most likely code word in the code book. If it's not, then let me try the second most likely noise effect. Remember, there are many noise effects, right? Which is why I had to code in the first place. If there was only one noise effect, I'd just subtract it and know it for sure and I'd be done. But there's a whole lot of noise effects, then, at least as long as it's not a huge number, I'm going to get through this pretty fast. And we'll see that indeed it is pretty fast. So the complexity is now a function of the noise. It's universal. I don't actually care what the code book was. My code book is just there to provide a code word membership check. Okay, so this is how we made a chip. which we just presented at the larger European Circuits Conference, ESS Circ. And it was actually selected as one of a handful of papers to be highlighted for long presentations. So, you know, this whole all these chips that I told you about, some of them which were already done, some of them which didn't exist yet, so our LC and CRC, we're able to get all of this into one chip. Okay, so we have the effect of the noise, which is additive, and we decode from that. So we have a micrograph, we do measurements, and I'm going to show you the outputs of those measurements. So first of all, what kind of codes do we have? I mentioned to you that we don't have that many codes available. I mentioned to you some Reed-Muller, Reed-Solomon. You know, these are classic codes of the, you know, the first type that I mentioned to you, like those linear codes, like algebraic and convolutional codes, block codes and convolutional codes. They're of that nature. So if you look at the different code lengths n and the different rates, there's only a few possibilities. These are the codes that are actually in the 3GPP 5G new radio control channel. These are polar codes with an added CRC. CA stands for CRC aided. You can see also only a few choices. Random linear codes, like Gallagher gave us in the 60s, 70s, you know, the world is your oyster. You know, it's like you can have as many codes as you want, right? There's no constraint. These are, by the way, this is the only time I'm going to show you these. It's not true. There'll be another one at the end. But, you know, this is how we as comms engineers talk to each other. We have an abscissa, which corresponds to the quality of the channel, usually to do with how much energy you use to transmit your signal. And you have something that sounds like, you know, blur, which is not exactly euphonious. Again, you know, it sounds like somebody is not very happy. They're having blur day, but it stands for block error rate, which actually stands for the probability that you decoded a code word incorrectly. So you can see here is the only thing I want to show you, what I want to bring your attention to is the dashed lines correspond to theoretical results for different code rates, different codes. These are codes that were doable up until now on existing chips. And the full lines show our experimental results. They match exactly the theory. Okay, so start with the theory and then see if you can do it. On the right, I'm showing you codes for which there were no hard decoders. Polar, CRC, polar, those were all with soft information, which I'll tell you a bit more about later. And also, again, encourage you to come to the talk this afternoon to hear more about. Again, they match exactly. In some of this, the theory was just that, was just theory, because there was not even an existing decoder on the, in all of the ones on the right. There was no existing decoder. So the same chip, one chip is doing everything, all the codes that were doable until now, and codes that nobody had been able to decode until now. I remember the peals of laughter from my colleague. You know, there you go. Is this using a lot of energy? No. We're not the lowest in energy usage. By the way, we compared here for codes which are high rate because these are for storage, because for communications, usually they use soft information, which I'll talk about later. But you can see we do all the codes, but I want to show you we are the lowest latency by a long shot per code word, okay, 1 microsecond. And we're not even using the most advanced chip technology. We're at 40 nanometers, which is great, but you know, nothing amazing. If you compare for short codes, these are the CRCA polar. In this case, the state-of-the-art decoder with soft information, with extra information that we don't use about the reliability of the different bits. Our chip does better than the state-of-the-art by a long shot. And if you look at using that extra soft information about, you know, the reliability, then we do a lot better than the state of the art. Okay, so soft information is information that comes from examining the signal itself in more detail. And we have a whole series of different grand algorithms, including soft grand, which shows that you can do the whole soft information. By the way, big plug here for students, even in comms, take algorithms classes. Take algorithms classes. Let me say it again. Take algorithms classes. You know, the whole point here was that we were able to take something which people thought was basically not possible and show that it had a heap structure, which we know how to deal with. This is what we teach our undergrads in CS in the sophomore years. It had a heap structure. It was manageable. So it went from being something that was thought to be not possible to something which is now being, you know, a few months after appearing, it was already being used in tutorials, not by us, by other people in major signal processing conferences as a state of the art. Okay. So very much in line with that. What kind of rates and lengths can we do? With, if you have this extra soft information about, you know, exactly what, you know, what the noise look like, not just zeros and ones, but let's say a more rich set of information about receiving. It turns out you can do, you know, long codes, you can do and you can do high rates. This is, by the way, the exact opposite from what traditional coding does. Usually to get high rates, they have to go to long codes. For us, you know, we can do low rates, but just with short codes, because again, it's not about the rate. It's not about the length. It's actually about the redundancy. Remember, I told you to say adding 2 bits to those 8 bits. It's about how many bits you added. Last thing I want to leave you with, we had a conversation before this, as I mentioned, with the Lytle family, and Louis Scharf also mentioned that Dean Lytle had done a lot of work on equalization. So equalization is a way of figuring out what the effect of the channel is. And the channel, as I mentioned before, is not clean. It's not just flipping my bits independently every so often. We make it look like that by taking these sort of messy noises and interleaving, you know, mixing it around to make it look like that. That mixing adds yet more delay, okay? And when I mean more delay, we're talking like a factor of 100. Okay, and remember, any delay I add, I have to pay for in bandwidth, because then I have to go faster. And remember, there's 10 billion, okay? So if you're doing a factor of 100, it means that you're only getting $100 million worth of your, you're getting $100 million worth of your 10 billion, okay? Here's an example of using GRAND with a little bit of statistical knowledge. And by the way, you know, Marin was talking about when we were meeting, and Eric mentioned, you know, these centers where you have data scientists, where you have people who do statistics, with people who do engineering, people who do computer science. This comes from the statistics, okay? You know, Ken leads a center on data science, okay? You take into account the statistics, and now what you see is that actually the more correlated the noise, the more structure it has, the faster, the better you can guess it. And so you're getting huge gains. Remember, this is how we talk to each other as comm engineers, right? The abscissa sort of going to the right is more expensive, going down is good, okay? So what you're seeing, this is always in dB, we talk in 10 log 10. So if you go from here to there, okay, which is now, this would be with, is a cost of 100-fold in delay, 100-fold. And B, you know, here you go from 0 EB over N0 to about 6. This is a cost of 4 in energy. Okay, so we can do 100 times better in delay, and we can reduce the energy by a factor of 4 by doing things intelligently. Okay. So use GRAND, do smart things faster with less energy, but keep drinking coffee, which is what I intend to do, although it's tea. Thank you very much. That gets me to the end of my hour, and I'm happy to take questions.
Thank you, Muriel, and let's thank Muriel for an excellent talk.
Thanks, I see that. I see people with their lighters, you know.
Yeah, so there are two ways we can do this. It'll be good to put the questions on the chat, as Eric has mentioned.
Yes, please pop them in the chat. Okay, great. Or raise your hand. Yes, use the visual chat. I'm going to try to view the gallery a little bit more fully. That way I can see if anybody has questions. And don't be shy. You know, one of the benefits of this remote setting is my ability to bite people is heavily curtailed.
So Sriram has raised his hand.
Yeah,
all right, go for it, Sriram.
You're a great talk. Thanks so much.
Thank you. Well, I know this is like, you know, it's like bringing coals to Newcastle to tell you about coding, but you know.
No, it's great, great talk. I had one question on the level of parallelism that it seems like your decoding can be massively parallel because, you know,
yes,
you can test all these code words in parallel. And you know what it reminds me of is Bitcoin mining, you know.
Okay, interesting.
When a miner is taking you know, whether they can find a block in Bitcoin. Basically, they try many hashes in parallel. And, you know, maybe this could be a way of doing energy efficient or useful mining, basically solving your brand decoding.
You know, it's very funny actually that you talk about mining. So what we do is we do a lot of parallelism and we check multiple possible noise effects in parallel. And as you said, you know, it's massively parallelizable. That's actually one of the ways we get this really fantastic delay, you know, and it's trivially parallelizable, right? Because you can check multiple noise effects at once. The funny thing about you mentioning mining is, remember I showed you these random codes, and I'll talk more about that in the talk this afternoon. Originally, we thought that we would be able to do code mining, right? We thought now that you have this way of decoding any old code, surely we should be able to find some fantastic codes, you know, and we'll just keep looking for great codes. And as you know, there's a lot of effort right now in using machine learning to construct codes and decoders, right? And we thought maybe this is another way to construct codes. And we were thwarted by the fact that almost every code is good. Like, they're all very good. The only codes we found that weren't fantastic, frankly, were polar codes without the CRC.
That's
everything else is great.
This is the information theory story actually first time playing out in reality.
Absolutely. So actually, it was funny because I was giving a talk at, and you know, by the way, if you want to see some of these codes, again, plug for the later lecture that I'm going to give. But you know, BCHs are fantastic. Reed Muellers are a little bit more flaky, which is, I guess, understandable because they're closer to polars. CRCs, which are usually not used for error correction, just error detection, are amazing. RLCs, amazing. Everything pretty much is amazing. Like, you have to go out of your way. And when I say random codes, you know, people said, oh, but you know, you must be like at least selecting the top 3 out of whatever. I'm like, 1 out of 3. No, no. Okay. When I mean random, remember that bag? That is literally the bag. It's just like whatever random seed generator your computer has, the first code that pops out is better than the state-of-the-art coders. So we were really pumped. We thought, oh, you know, we'll do this mining, and every so often we'll put out a new code book and it'll be exciting. As you said, you know, the story that we heard from 1948, it was true.
Wow,
so when I
give you a twist in the story.
So, you know, that whole machine learning around building codes, which also at the beginning, I was like, oh, this is going to be great. I mean, you know, just so, yeah, I spent a lot of my youth, misspent a lot of my youth on coding. Okay. I teach machine learning to undergrads. I'm like, jackpot, I'm going to put the two together. And this is like, no, there's nothing to be done there. There's nothing to mine. It's like, you can't step without, you can't take a step without stepping on a code book that's good. Literally, they're all good, except for a few, and you really have to go out of your way to construct them. So, no need to machine learn to create good codes. Just so as I mentioned, I was giving the inaugural distinguished lecture at Bilkent University where Erdal Arakan is, and he said, that swoosh that you have, you should actually put a line back because it's really back to the beginning, right? Those random codes. Now that we know, we've known since the 60s, 70s, the ledger's not the problem. It's the decoding. There's no, it's been a surprise. I have to tell you, we were shocked. I mean, I knew it intellectually, but because there was such a prejudice against being able to do this, like, who do you think you are to be able to do this? That was one of the reasons to go to the chip for it, by the way. There's nothing like, okay, here you go, have the chip. Go try it,
There's a question in the chat if you want to read it, Radha.
Yes. In the presentation, you mentioned improvements to average latency, which were excellent. The impact to tail latency. Yeah, actually, we do have results, and let me pop those up. About the decoding latency. So the worst case decoding latency is somewhat worse than this, but it's like 1 in 1,000 times you'll get a longer latency. And then what I would say is I would encourage you to come to the talk this afternoon. I'll go a little bit more into that. Okay. That being said, you can control the latency, it turns out, with something called grant with abandonment, where you just abandon, if it's taking too long. And there's an extra benefit to that. When you're taking a long time to decode, it's because your noise has had a bad realization, which means that actually your probability of being wrong is increasing as the time that your decoding goes up. So in terms of the delay, you're getting worse and worse reliability as you take more time to decode. So you're better off stopping, not decoding, because otherwise, if you take too long, it also means that you're less and less sure that the code word that you're going to give is the right one. So it's better for you not to keep pushing. Sure, you can give me the maximum likelihood, right? But it's a maximum likelihood with bad likelihoods, okay? It's like, bad odds at that point that you actually got something correct, which, by the way, gives you another thing, which I didn't mention about. We talked about capacity, that 1 minus h. We always think, okay, you have to, you shouldn't transmit above capacity, disaster, here be dragons. And it turns out you can actually transmit a lot above capacity, often above capacity. If you decode it quickly, it's still likely that you'll find the right code word. Okay, so we usually think about probability of error, but if you're sort of, an invertebrate, and not to say, pathological optimist like me, you can think of probability of success. Okay, and actually your probability of success is really, really good, even if you're above capacity, unless you're like super, like ridiculously above capacity, which means that also temporary changes in your system, you don't have to react as quickly to them. Okay, and again, that goes into the latency. So allowing higher, waiting for longer is actually getting you into the danger zone. I hope that was from Matt. Did that answer your question, Matt?
Yeah, it looks like Matt has some.
Yeah.
Yeah, there is another comment or question from Kalev. Sep?
Great. Can GRAND be readily used in wired datacom like IEEE data? That's a really good question. It's interesting. Actually, you're like the third person to ask me this in 2 weeks. And certainly, data center standards tend to have, very low bit error probabilities. And as I mentioned, it's really about the amount of redundancy. So even if you have a long code, if you don't have a lot of redundancy, you're fine. So while we haven't done a strong consideration of it, we've started looking at it because my impression is that we could. I worked in data centers on the commercial side for a long time. I haven't for a few years right now. I've done a lot of, but I did a lot of consulting data centers. So my impression without having, just from memory, but it's like, 7 years at this point or so, is yes. That's a great question, Caleb.
Any other question for Muriel?
Okay, I think that we will call it because we're nearing the end of our time. So thank you for such a grand talk.
Thank
you. Couldn't help it. And thank you everyone for joining us today for the 14th annual Lytle lecture. Thank you, Radha, and thank you, Mariam, for chairing the Lytle Lectureship Committee. And of course, thank you to Muriel for your great talk. I'd also like to thank the UW ECE events and advancement teams for organizing this event. And once again, thank you again to all who have contributed and continue to make gifts to the Lytle Lecture Fund. We are very grateful for your support. And as Muriel reminded us a few times, I'll remind you again, if you want to dive deeper into this topic, attend the technical seminar today, which is at 2 to 3 p.m. via Zoom, and links should have been sent all over email at this point. And I think you might be able to find them on our webpage. So once again, thank you, Muriel, and thank you all for attending, and have a fantastic day.
Thank you all, and thank you again to the Lytle family. I think I see Marilyn.
Yep, there she is.
Good to see you. Thank you for attending. Take care, everyone. Bye-bye.
Bye.